Alright guys, welcome to the web lesson that I'm posting for Wednesday's lesson. Sorry that we can't be in class together, but I hope you guys are enjoying your snow day. It's currently about 11 p.m. right now, and it is thunder snowing outside. I didn't even know thunder snow existed until earlier this week, but it's kind of interesting. Hope you guys are all staying safe also and staying off the roads at the moment. Anyway, let's jump into the lesson for today. What I'm going to do is I'm going to try to make this a little bit quicker than a normal lesson because if at any point you need me to repeat something, you can always just rewind the video. And if at any point I'm going a little bit too fast, then you could just pause and catch up with your notes, and then press play when you're ready to have me continue on. Or I guess in theory you could put me on mute and just watch the math on the screen. The other thing that I've done is I put a copy of the notes on the web that you guys could print out so that you don't have to be scribbling things down as we're going through this PowerPoint. So hopefully this will go a little bit faster than usual. We'll see, right? All right, so we are continuing on with our discussion of Taylor series. And really basically what I'm going to do is we have the theory of Taylor series down. And so I'm just going to talk about a few examples that we can work out, some applications of Taylor series, and it's going to be light on theory and more on applications to different kinds of problems. First thing I wanted to do was kind of build on what we did yesterday, which was we developed a Taylor series for the sine of x, and we used that kind of general recipe for finding a Taylor series for a function. We took lots of derivatives and we used those for the order n term. Each of the order n terms, we used another derivative to get that term. We could theoretically do the same thing right now to get the cosine function, to get a Taylor series describing cosine. However, that's not what we're going to do. Instead, what I'd like to do is take the one that we found for sine. So remember that we had a Taylor series for sine, and that Taylor series was sine of x equals x minus x cubed over 3 factorial plus x to the 5th over 5 factorial, etc. So we have alternating signs, and we're counting up by even powers and even factorials in our denominator. If you want to write that in summation notation, that's the sum from 0 to infinity of negative 1 to the n times x to the 2n plus 1 all over the quantity 2n plus 1 factorial. We're going to take this guy that we kind of developed in class, and we're just going to do a quick little calculus trick to figure out what the Taylor series for cosine has to be. And this is kind of a general technique for Taylor series that's very useful. If you remember from earlier in your calculus career, the derivative of the sine is the cosine. So we should be able to just take this Taylor series we found, take the derivative of both sides, term by term differentiation, and that should give us a Taylor series for the cosine. That's what we're going to do. So to find cosine, we could just take the derivative of the work we already did rather than building this from scratch. And this is called term by term differentiation. That just means for an infinite series to find our derivative, we're just going to take each derivative, the derivative of each term individually. So I'm going to take the derivative of the sine of x on the left side to get cosine of x. And then on the right side, I'm going term by term, so the derivative of x is going to be 1. The derivative of x cubed over 3 factorial, well, I know that this is going to go to x squared over, let's see, this power of 3 is going to become a coefficient. But if you think about it, that power of 3 that became a coefficient, that 3 is going to knock out one of the 3 from the 3 factorial, leaving it as 2 factorial. Likewise, when this 5 comes down and becomes a coefficient, that 5 is going to knock out the 5 from 5 factorial, leaving us just with a 4 factorial. And so on and so forth. We're just going to follow that pattern. Plus dot dot dot. And so you can see that in just a couple steps, just doing a couple of derivatives, we were able to figure out what the Taylor series for the cosine, or actually I guess the Maclaurin series for the cosine of x is. Since we're centered at the origin here, we can call this a Maclaurin series for the cosine of x. Okay, I could summarize this on the next slide. So we have our sine formula from yesterday. We have our cosine formula from today. And notice that for both of these series, we converge for all x's in the set of real numbers. Another thing that you guys might notice, if you recall from your trigonometry class, the sine of x we determined was what is called an odd function. And the reason it's called an odd function is it has this property that the sine of negative x equals negative sine of x. We defined that property to be a property of odd functions. And then the cosine of x, if you recall, is an even function because it has the property that the cosine of negative x equals positive cosine of x. Okay, why am I bringing this up right now? Well, what you can do is you can look at these Taylor series, and you could see that that same relationship, you know, the oddness of sine or the evenness of cosine, is apparent in its Taylor series expansion as well. If you were to plug negative x in for sine of x, that would give you negative sine of x. And the way you can tell is if you put negative x in for any of these odd powers of x, that's going to make that term into its opposite. On the other hand, for cosine, look at all of these even powers of x. If I was to plug negative x in into the cosine of x, all of these even powers of x would not make a difference with plugging in a negative. Negative x quantity squared, it doesn't change the sign of the term. Negative x quantity to the fourth power, it won't change the sign of the term. And the reason that I'm mentioning this is, first of all, it's important to know that the properties of the original function are going to be carried over into the properties of the Taylor series, or the Maclaurin series in this case. But the other thing is, I think it's a useful tool for remembering the sine expansion and the cosine expansion. I think it's easy sometimes to mix up a Maclaurin series for sine and for cosine because they look similar. They have a lot of things in common, alternating signs, and powers that are counting up by 2 each time. So one way to make sure that you don't get them mixed up is to remember cosine is even and all of these powers are even. Sine is odd and all of its powers are odd. So just a nice way to remember your Taylor series for sine and cosine. Okay, so I checked my email late this evening and I didn't have any emails from anybody regarding homework. And I was hoping to maybe have a couple questions, but instead, since I didn't have any questions, I just kind of picked a couple from the homework assignment. They're actually pretty quick, so hopefully this will help you guys with the assignment that you were working on last night. And I think it should also help with the homework that you guys are going to work on tonight to have ready for school on Thursday. Okay, the first one I had was number 5 from section 9.2. It says construct the first 3 non-zero terms and the general term of the Maclaurin series generated by the function and give the interval of convergence. So they gave us some function, in this case sine of 2x, and they want the Maclaurin series. And they want you to kind of come up with a couple of the first couple terms in that Maclaurin series and a general term that's, you know, in terms of n. Okay, first thing that I'm going to do is I'm going to say, well, I don't know much about the sine of 2x, but I know a lot about the sine of x. The sine of x we've already derived in class is x minus x cubed over 3 factorial, plus x to the 5th over 5 factorial, minus x to the 7th over 7 factorial, etc. Which, by the way, for now, you guys might be looking these up in your notes when you need them on your homework. By the time we finish this chapter, these are going to need to be memorized. It's really important that the basic trig functions, sine of x and cosine of x, you need to have their Maclaurin series memorized. E to the x we're going to have to memorize. Natural log of 1 plus x we're going to have to memorize. The inverse tangent of x we have to memorize. And then there's 2 others, 1 over 1 plus x and 1 over 1 minus x are also important to memorize. Just to kind of throw that out there so you know that's something that's expected of you. I don't want it to seem like a surprise to anybody. In any case, so we're starting with an unfamiliar function. and we're going to compare it to one that's more familiar. And the kind of beautiful thing with this theory is the way to get from one to the other, to get from the unfamiliar one, or from the familiar one to the unfamiliar one, is we just substitute. So if I take my sine of x Maclaurin series, if I replace all of the x's with 2x, that'll do the trick. So instead of x for my sine of x expansion, I'm going to put 2x in there. And here's the cool thing, we're done. There is nothing else to do on this problem. If you really wanted to, I suppose you could express 2x quantity to the 2n plus 1. You could express that as 2 to the 2n plus 1 times x to the 2n plus 1. But I don't really see any reason to do that. So I wouldn't. I would leave it as 2x quantity to the 2n plus 1. And one thing to remember is your interval of convergence is still all real numbers. Replacing x with 2x is not going to be changing that. Okay, so that's number 5 taken care of. I'm going to take us on to number 11 from last night's homework.